All right, hello there. So this is a novel approach to theoretically perhaps capture antiparticles and particles and then study them, perhaps. So basically, the Casimir effect helps us to create or find these virtual particles that come into existence, and they're basically these pairs of an antiparticle and a regular particle, and they just disappear really quickly. So this takes two things that can occur, which is the Zeno effect, which when you are measuring something consistently, it stays in that state of permanent wherever or something. And so if we were to find a way, which this will explain, how to create those particles and then trap them, then perhaps we can do something with them. So this is how it works.
A theoretical exploration of a Casimir-Zeno particle trap for nanoscale manipulation, abstract. This paper explores the theoretical framework for a novel device, the Casimir-Zeno Particle Trap, designed to manipulate and study particle-antiparticle pairs created via the Casimir effect. By combining the Casimir force with the quantum Zeno effect, we propose a method to trap, stabilize, and potentially manipulate these fleeting particles at the nanoscale. This concept, while highly speculative and facing significant technological hurdles, could open new avenues in fundamental physics research and potentially lead to breakthroughs in materials science and quantum technologies. 1. Introduction. The quantum vacuum, far from being empty, is a dynamic arena of virtual particle-antiparticle pairs constantly fluctuating in and out of existence. Harnessing these fluctuations could revolutionize our understanding of fundamental forces and offer unprecedented control over matter at the smallest scales. This paper proposes a theoretical framework for a device that combines the Casimir effect, which generates an attractive force between closely spaced conductors due to vacuum fluctuations, with the quantum Zeno effect, which can freeze the evolution of a quantum system through frequent measurements. The goal is to create a trap that stabilizes particle-antiparticle pairs long enough for study and manipulation. 2. Casimir force generation. The Casimir effect arises from the alteration of vacuum fluctuations by the presence of conducting boundaries. For two parallel plates of area A separated by a distance d, the Casimir force F_c is given by F_c equals fric p squared bar. C240D caret 4a, where g is the reduced Planck constant, c is the speed of light. For nanoscale separations, e.g. d approximately equals 1 nanometer, the force can be significant, on the order of nanonewtons for micron-sized plates. Precise control over the cavity dimensions and surface properties is crucial. Materials with high conductivity, e.g. gold, aluminum, are preferred, but exploring superconducting materials at cryogenic temperatures could further enhance the effect by minimizing losses. Atomic layer deposition, ALD, offers the necessary precision for controlling the gap distance and ensuring atomically smooth surfaces, minimizing deviations, delta D, that exponentially affect the Casimir force, delta F_c proportional delta D/d. 3. Quantum Zeno measurement setup. The quantum Zeno effect describes the slowing down of quantum evolution through frequent measurements. In our trap, this would be achieved using embedded quantum dots or qubits, superconducting transmon qubits, with a Hamiltonian. H equals 4, E_c, N_G, squared dash E_j cos phi, where E_c and E_j are charging and Josephson energies. N is the number of Cooper pairs, N_g the offset charge, and phi the phase across the junction, are promising candidates. The Zeno effect manifests as a modification of the decay rate, gamma, of a quantum state under continuous observation. The survival probability P of t can be approximated as P of t approximately equals, express, gamma t1 fract _mt_m plus t, where t_m is the time between measurements. Ultrafast measurement pulses, potentially from femtosecond lasers, are required to outpace the decoherence time of the quantum system. Highly efficient single-photon detectors, potentially superconducting nanowire single-photon detectors, are needed for readout with high fidelity. 4. Particle trapping and manipulation. Beyond the Casimir force and the quantum Zeno effect, additional confinement might be necessary. Nanoscale Paul or penning traps, utilizing electromagnetic fields described by the Lorentz force law.
F_, EM rovná se Q vic E plus vic V times vic B,
where Q is the particle's charge, V its velocity, E the electric field, and B the magnetic field, could be integrated into the structure. The ultimate goal is to manipulate the trapped particles. This is the most speculative aspect, potentially involving quantum electrodynamics to manipulate vacuum fluctuations or induce pair production with high-energy photons or fields. 5. Challenges and considerations. Several significant challenges must be addressed. Decoherence. Maintaining coherence in the qubits and trapped particles is paramount. Cryogenic temperatures, achievable with dilution refrigerators, T proportional 1/√τ_c, where τ_c is the coherence time, are essential. Measurement back action. Minimizing the disturbance caused by measurements is crucial. Quantum non-demolition, QND measurements, could be a potential solution. Fabrication complexity. The fabrication of such a complex nanostructure demands significant advances in nanofabrication techniques, possibly including molecular beam epitaxy, MBE, for precise material control. Theoretical understanding. A deeper understanding of the interplay between the Casimir effect, the quantum Zeno effect, and particle-antiparticle creation in confined geometries is crucial. Further research in quantum field theory is needed. 6. Conclusion. The Casimir-Zeno particle trap represents a highly ambitious, yet potentially groundbreaking concept. While significant technological and theoretical challenges remain, its realization could revolutionize our ability to probe the quantum vacuum and manipulate matter at the nanoscale. This paper provides a theoretical roadmap for future research and development in this exciting field.
Well, there you have it. Some further development and see what happens.